Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today's lesson in general chemistry introduces two big ideas: atomic structure and electromagnetic radiation. We're going to start by looking at the historical development of atomic models, beginning with Dalton's solid sphere model and then working our way up to the quantum mechanical model. We're going to see that the quantum mechanical model describes electrons in terms of probabilities rather than exact location. Then the question becomes, why do we care so much about electrons? Well, as chemists, electrons are incredibly important because they determine how atoms bond, how they react, and how they interact with one another. And how do we study electrons? Well, through the energy they exchange, which happens in distinct packets called photons. Photons are the building blocks of electromagnetic radiation, and that's really the focus of today's lesson. So by the end of this, we're going to dive into the properties of waves, things like wavelength, frequency, and energy, and then use these ideas to understand how electromagnetic radiation interacts with matter. With that introduction out of the way, let's begin by talking about atoms. Atoms are the fundamental building blocks of all matter. An atom is the smallest unit of an element that retains the properties of that element. At its core, the atom has a dense nucleus that's composed of protons, which carry a positive charge, and neutrons, which are neutral. Surrounding the nucleus are negatively charged electrons, which occupy vast regions of space compared to the size of the nucleus itself. Together, the protons and neutrons determine the mass of the atom, while the electrons, with their arrangement and movement, define the atom's chemical properties and its reactivity. But how did we come to understand this structure? Our current understanding is the result of centuries of scientific work, with contributions from many scientists who helped shape our knowledge step by step. It all started in 1803 with John Dalton. He introduced the concept of the atom as an indivisible particle, like a solid sphere. And his model is often called the billiard ball model. And it suggests that atoms of different elements vary only by their mass. Now, while this was groundbreaking at the time, it didn't account for the internal structure of the atom. That changed in 1898 when J.J. Thomson discovered the electron through his experiment with cathode ray tubes. His work demonstrated that atoms contain negatively charged particles, and this led to what's called the plum pudding model. In this model, the atom was seen as a positively charged sphere embedded with tiny negatively charged electrons, kind of like raisins in a pudding. A few years later, in 1911, Rutherford refined this view with his famous gold foil experiment. So by observing how alpha particles scattered when they were directed at a thin sheet of gold, Rutherford showed that atoms are mostly empty space with a dense positively charged nucleus at the center. This led to the nuclear model of the atom, and this started a pivotal shift in our understanding of atoms. Then came Niels Bohr, who in 1913 proposed that electrons orbit the nucleus in defined paths or shells. His model offered an explanation for the discrete energy levels that were observed in atomic spectra. And this was a significant leap forward, but it still couldn't fully explain the behavior of electrons. Finally, we arrive at the modern quantum mechanical model. This model shifts our perspective entirely. So instead of imagining electrons as tiny particles that follow fixed orbits, we describe them as existing in regions of probability that we call orbitals. This kind of model acknowledges the wave-like nature of electrons, and it is currently the most accurate representation we have of atomic structure. So now that we've built an understanding of the structure of an atom, let's shift our focus to what drives chemistry, the electrons. So while protons and neutrons remain relatively fixed within the nucleus, electrons, they behave very differently. They don't have fixed positions, but instead they occupy regions of space around the nucleus. These electrons, they can move between energy levels when they interact with energy. So when an electron absorbs energy, it moves to a higher energy level that's further away from the nucleus. And this process is called excitation. However, the excited state is unstable, so the electron will eventually return to a lower energy level, releasing energy in the process. And this is called relaxation. But how does this energy transfer actually occur? Well, it happens through the absorption or emission of specific packets of energy called photons. So these packets are quantized, meaning they carry fixed amounts of energy that's going to be determined by their frequency. So if an electron absorbs a photon, it gains exactly the right amount of energy needed to move to a higher energy level. On the other hand, when an electron releases energy, it emits a photon. And this photon's energy is going to correspond exactly to the difference between the two energy levels. Now, this precise and predictable energy exchange is really important in chemistry because it allows us to measure and understand how atoms interact with energy. Now, here's an important perspective on photons. Photons, they behave both as particles and as waves. This duality, being discrete energy packets while also being part of a wave, is what makes photons so unique. Photons are packets of electromagnetic radiation, and every form of electromagnetic radiation, from radio waves to gamma rays, is made up of photons. The electromagnetic spectrum essentially categorizes all forms of electromagnetic radiation by their wavelength and frequency, with each region corresponding to photons with different properties and interactions. Photons are also responsible for the way electromagnetic radiation interacts with matter. Higher energy photons can break chemical bonds or ionize atoms, while lower energy photons can cause things like molecular vibrations or rotations. So taking all that into consideration, the main point I want to make here is that electromagnetic radiation doesn't behave purely as a particle or purely as a wave. It exhibits both behaviors. When electromagnetic radiation interacts with matter, it behaves like particles and it transfers energy through photons. But when electromagnetic radiation travels through space, it behaves like waves with oscillating electric and magnetic fields. And this dual nature of electromagnetic radiation is a cornerstone of modern physics and chemistry. Now that we've discussed photons and their role in the particle-like behavior of electromagnetic radiation, let's move on to the concept of waves to understand the wave-like behavior of electromagnetic radiation. Electromagnetic radiation is a form of energy that travels through space at the speed of light, which is approximately 2.99 times 10 to the 8 meters per second. Now, in the course you're taking with me, we can approximate this to 3 times 10 to the 8 meters per second when we carry out our calculations. Now, this energy, it's carried by oscillating electric and magnetic fields that move perpendicular to one another and propagate as waves. And these waves are fundamental to understanding how energy interacts with matter. So to describe waves, we use 3 key characteristics: wavelength, frequency, and speed. Let's go through each of these step by step. Wavelength, represented by the Greek letter lambda, this is the distance between 2 consecutive peaks or 2 consecutive troughs in a wave. So you can think of it as the length of one complete wave cycle. Wavelength is typically measured in meters, but depending on the type of electromagnetic radiation, we often use smaller units like nanometers. 1 nanometer is equal to 10 to the minus 9 meters, or we can even use picometers. 1 picometer is equal to 10 to the minus 12 meters. Then we have frequency. This is represented by the Greek letter nu. This refers to the number of wave cycles that pass a given point in space per second. It's measured in units of hertz, where 1 hertz equals 1 cycle per second. So hertz is equal to inverse seconds, essentially. Now, a higher frequency means more waves are passing a point in a given time, which usually corresponds to shorter wavelengths and higher energy. More on that in a second. But let's also talk about speed. In a vacuum, all electromagnetic waves travel at the same speed, and this is referred to as the speed of light. We said this was approximately 3 times 10 to the 8 meters per second. This is a universal constant, but the relationship between wavelength and frequency determines the specific characteristics of a wave. And that leads us to 2 important equations. Now, the relationship between these 3 properties, wavelength, frequency, and speed, are demonstrated and given by this equation right here. This equation tells us that the speed of light, c, is equal to the product of the wavelength and the frequency. This means that if the wavelength of a wave increases, its frequency must decrease to keep the speed constant, and vice versa. Now let's break this down a bit more. Imagine you're solving a math problem where 2 numbers multiply to equal a fixed value. For example, 10 is equal to 5 multiplied by 2. Let's say we increase one number. Let's say that we increase 5 to 10. By doing that, we have to decrease the other number to ensure that our total still equals 10. So 2 here has to decrease to 1, and 10 multiplied by 1 is 10. So that's good. We ensured that the final answer was still 10. But by increasing one of those values, increasing 5 to 10, we had to decrease 2 to 1 to ensure that the product was still 10. And the same principles apply here for this equation. The speed of light is like a fixed value in our example. It doesn't change. If the wavelength of an electromagnetic wave increases, meaning the waves stretch out and the distance between peaks become longer, then the frequency must decrease, meaning that there are fewer waves that will pass a point per second. This ensures, again, that the multiplication, that the product of these two values equals the speed of light, which is a fixed value. And the inverse is also true. If the wavelength becomes shorter, so it decreases, then the frequency must increase to compensate for that change and ensure that the product of these two values still equals the speed of light. This inverse relationship between wavelength and frequency, super important to understanding how waves behave. Longer wavelengths correspond to lower frequencies, while shorter wavelengths correspond to higher frequencies. Now, energy is another important property of electromagnetic waves. The energy of a photon is directly proportional to its frequency, and it can be calculated using this equation. This equation says that the energy is equal to Planck's constant. Planck's constant is equal to 6.626 times 10 to the negative 34 joules times second. And that Planck's constant is multiplied by frequency. Now we can rewrite this equation by replacing the frequency term with the speed of light divided by lambda. And we got this relationship simply by rearranging this equation. This equation says that the speed of light is equal to wavelength multiplied by frequency. If we want this expression to solve for frequency, we just need to divide both sides by wavelength. This gives us the following equation. Nu, or frequency, is equal to the speed of light divided by wavelength. And we went ahead and took this relationship and plugged it into here for frequency. So now we have two ways of calculating energy. One that depends on frequency information, and the other that depends on wavelength information. Now, to visualize this, let's look at the electromagnetic spectrum again. This spectrum is essentially a range of all types of electromagnetic radiation organized by their wavelengths and frequencies. At one end, you have gamma rays, which have very short wavelengths, high frequencies, and high energy. At the other end, you have radio waves, which have long wavelengths, low frequencies, and low energy. In between, you'll find other familiar types of radiation. We have X-ray, ultraviolet, visible, infrared, and microwave. Notice that as you move across the spectrum, going from gamma rays to radio waves, there is an increase in wavelength. Similarly, you'll notice that there is a decrease in frequency and a decrease in energy. We know that this is true because, first and foremost, there is an inverse relationship between wavelength and frequency. Since wavelength increases going from gamma to radio waves, then frequency must decrease. Now, why does energy decrease as well? Well, from this equation right here, we know that energy and frequency are directly proportional. So when frequency decreases, so does energy. When frequency increases, so does energy. Therefore, moving from gamma rays to radio waves in this direction, there's an increase in wavelength, a decrease in frequency, and a decrease in energy. If we were to move in the opposite direction, if we go from radio to gamma rays, then this is just going to be the inverse trend. Wavelength is going to decrease, and frequency and energy will increase. One particularly important section of the electromagnetic spectrum is visible light. This is the portion of the electromagnetic spectrum that our eyes can detect. This range spans wavelengths from approximately 400 nanometers to 700 nanometers. And within this range, wavelength determines the color of the light we perceive. For example, shorter wavelengths around 400 nanometer correspond to violet and blue light, while longer wavelengths around 700 nanometer correspond to orange and red light. Then colors like green and yellow fall in between. We're going to revisit the electromagnetic spectrum shortly to explore each region in greater detail, but for now, let's jump into some practice problems. This first problem says, an electron moving from the third energy level to the first energy level will blink. A says emit a photon. B says absorb a photon. C says change elements. And D says absorb energy. Electrons in an atom, they occupy energy levels which are quantized. The first energy level is the lowest energy level. It's known as the ground state, while higher energy levels like the third energy level are excited states. Electrons lose energy by emitting a photon, and a photon carries the exact amount of energy corresponding to the difference between the two energy levels. This energy is released as light or another form of electromagnetic radiation when an electron moves from a higher energy level to a lower energy level. So the correct answer for problem 1 is going to be A, emit a photon, because the electron is losing energy as it moves from the third to the first energy level. B is incorrect because absorbing a photon is what would happen if the electron were moving up to a higher energy level, because that requires gaining energy. C is incorrect. Changing elements involves altering the number of protons in the nucleus, not electron transition. So this is irrelevant here. And D says absorb energy. Moving down energy levels releases energy, not absorbs it. So this is also incorrect. Once again, the correct answer for problem 1 is A. Problem 2 says, compared to a 620 nanometer wavelength, a 760 nanometer photon has blink. And in the answer choices, we see that we're comparing wavelength, frequency, and energy. The key equations to remember for this problem are the speed of light is equal to wavelength multiplied by frequency, and energy is equal to Planck's constant multiplied by frequency, and this is also equal to Planck's constant multiplied by the speed of light divided by wavelength. From the first equation, we know that wavelength and frequency are inversely proportional. This means that the longer the wavelength, the lower the frequency. From the second equation, we know that energy and frequency are directly proportional, and energy and wavelength are inversely proportional. Now, the wavelength, 760 nanometers, is longer than 620 nanometers. A longer wavelength corresponds to a lower frequency, and a lower frequency results in lower energy. And that makes the correct answer for problem 2, D. Compared to a 620 nanometer wavelength, a 760 nanometer photon has a longer wavelength, lower frequency, and lower energy. Let's tackle example problem 3. This problem says, what is the frequency of light with a wavelength of 3 meters? Here we're going to use the following equation. The speed of light is equal to wavelength multiplied by frequency. And we're going to rearrange this equation to solve for frequency. So we're going to divide both sides by wavelength. This gets us that frequency is equal to the speed of light divided by wavelength. We know both of these values. C is a constant, and it's equal to approximately 3 times 10 to the 8 meters per second. And we're given wavelength in the problem. That's equal to 3 meters. Here for our units, meters are going to cancel out. So our final answer is going to have units of 1 over seconds. This is good. This is equal to hertz, which is the units for frequency. And then we're going to carry out this calculation. Now, this is a really easy calculation to do because the 3 in the numerator cancels out with the 3 in the denominator. And now we're just left with 1 times 10 to the 8. So the answer here is that frequency is equal to 1 times 10 to the 8 hertz, which is answer choice B. Beautiful. Now let's go back and reiterate how electromagnetic radiation propagates through space. This part is just to provide clarity on electromagnetic radiation and its wave-like behavior. And I think reiterating content is super important, especially in a difficult course like chemistry. Again, we said electromagnetic radiation is a form of energy that travels as waves composed of both electric and magnetic fields. And these fields oscillate perpendicular to each other and to the direction of wave propagation. As the electric field oscillates in one plane, it creates a changing magnetic field in a perpendicular plane and vice versa. And this constant interplay between electric and magnetic fields allows the wave to self-propagate through space without the need for a medium, which is why electromagnetic radiation can travel through the vacuum of space. It's also important to note that electricity and magnetism are inherently connected. They are two aspects of the same phenomenon. This is why electromagnetic radiation can be described as oscillating electric and magnetic fields traveling together. Now, I'm not going to test you on electric or magnetic fields. That's for your physics classes, but I just want you to have some sort of imagery about electromagnetic radiation as it propagates through space. Now, let's take a moment to understand another key property of waves, and that is interference. When two waves overlap, they interact with one another, and this interaction can take two forms. It can be constructive interference. This occurs when the peaks of one wave aligns with the peaks of another, effectively combining together to create a larger wave. This results in an increase in amplitude, which corresponds to greater intensity. We can also have destructive interference. This occurs when the peaks of one wave align with the troughs of another. And in this case, the waves cancel each other out, reducing or even completely eliminating the amplitude. So far, we have discussed photons, we've discussed waves, we've discussed electromagnetic radiation. What is the connection and what is the takeaway message? It's this. If there's anything you take away from this lecture, it is this. Photons are the quantized packets of energy that make up electromagnetic radiation. They carry energy in fixed amounts, and they have properties like frequency, wavelength, and energy that determine how they interact with matter. Photons represent the particle-like behavior of electromagnetic radiation. Electromagnetic radiation is also a wave of oscillating electric and magnetic fields traveling through space, even in a vacuum. This wave-like nature allows electromagnetic radiation to propagate, and it explains phenomenon like interference. Together, the particle and wave descriptions define the dual nature of electromagnetic radiation. When electromagnetic radiation interacts with matter, it behaves like particles, and it transfers energy in quantized packets called photons. When electromagnetic radiation travels, it exhibits its wave-like behavior, propagating through oscillating fields. And finally, the electromagnetic spectrum organizes all forms of electromagnetic radiation, from low-energy radio waves to high-energy gamma rays. And each region of the spectrum corresponds to photons with different wavelengths, frequencies, and energies. With that, let's shift our focus to the practical significance of these interactions. Why do we, as chemists, care about electromagnetic radiation? Well, because different regions of the electromagnetic spectrum interact with matter in ways that reveal really important information about atomic and molecular structures. For example, radio waves interact with atomic nuclei, and it causes them to spin. This is the basis of techniques like nuclear magnetic resonance, NMR, which chemists use to determine molecular structures, and it's the basis for magnetic resonance imaging, MRI, which creates detailed images of soft tissues to help doctors diagnose conditions. Microwaves, they cause molecules to rotate. In everyday life, this explains how microwave ovens heat food by exciting water molecules to spin and generate heat. Infrared radiation interacts with molecules by causing vibrations within chemical bonds. This is the foundation of Fourier transform infrared spectroscopy, also known as FTIR. This is just another tool used in chemistry to study molecular structures. Infrared also has applications in medicine, such as detecting blood flow or inflammation, and it has applications in astronomy, where it's used to study heat emitted by distant stars and planets. Next up, we have visible and ultraviolet light. The visible and ultraviolet light photons are energetic enough to excite valence electrons in atoms and molecules. And this kind of interaction is really essential for understanding electronic transitions. UV photons in particular can ionize molecules, which is why UV or ultraviolet radiation can cause damage to materials like DNA. Finally, let's discuss X-rays and gamma rays. These are the most energetic forms of electromagnetic radiation. X-rays can penetrate deeply into materials and actually interact with inner shell electrons, and that makes them really critical for X-ray crystallography. X-ray crystallography helps reveal the structures of things like proteins and DNA, and it's also useful for imaging bones in medical diagnostics. Gamma rays, with their even higher energy, are used in cancer treatments because they can target and destroy cancer cells. With that, we have ended the lecture portion of our discussion today. What we're going to jump into is a couple more practice problems that we're going to do together. This first problem says, what is the energy of a 300 nanometer photon? To solve this problem, we're going to use the following equation. Energy is equal to Planck's constant multiplied by the speed of light, and that's all divided by wavelength. Planck's constant is equal to 6.626 times 10 to the negative 34 joules times second. C, that's the speed of light. This is approximately 3 times 10 to the 8 meters per second. And lambda, or wavelength, is given to us as 300 nanometers. So let's go ahead and plug these values into the equation. This gives us 6.626 times 10 to the negative 34 joules times second. That's going to be multiplied by the speed of light, 3 times 10 to the 8 meters per second. And that's going to be divided by the wavelength, which we're given as 300 nanometers. Now, energy is expressed in units of joules, so we want all our other units to properly cancel out. Seconds cancel out, but here we have meters and nanometers. We want these to match so that they properly cancel out. So what we're going to do is we're actually going to convert 300 nanometers to meters. 1 nanometer is equal to 10 to the minus 9 meters. So we can simply rewrite this as 300 times 10 to the minus 9 meters. If we plug this into our calculator, we're going to get that the energy of a 300 nanometer photon is equal to 6.626 times 10 to the negative 19 joules. So that is how we solve problem 4. Let's tackle this next one. This problem says, what is the energy of a photon with a frequency of 3 times 10 to the 19 hertz? For this problem, we're going to use the following equation. Energy is equal to Planck's constant multiplied by frequency. Again, Planck's constant is equal to 6.626 times 10 to the negative 34 joules times second, and frequency is equal to 3 times 10 to the 19 hertz. This is what we're given in the problem, and alternatively, we can write this as 3 times 10 to the 19, 1 over seconds. Hertz is equal to 1 over seconds, and if we write it in this way, our units are properly going to cancel out so that we can get energy in units of joules. So let's go ahead and plug this into our equation. 6.626 times 10 to the minus 34 joules times second is multiplied by 3 times 10 to the 19 inverse seconds. The seconds cancel out. Our final answer is going to have units of joules. If we plug this into a calculator, we should get 1.99 times 10 to the minus 14 joules. Beautiful. The next problem says, what is the correct order of increasing energy? Remember that energy increases as wavelength decreases and frequency increases. The order from lowest to highest energy is microwave, visible light, ultraviolet, X-rays, then gamma rays. So the correct answer for this problem is answer choice A. The next problem says, when a given molecule absorbs a photon of infrared radiation, blank. A says it begins to vibrate. B says it promotes electrons into delocalized bonding orbitals. C says it begins to rotate. And D says its electrons are excited to higher energy levels. When a molecule absorbs a photon of infrared radiation, it gains energy that causes vibrational motion within its chemical bonds. Infrared radiation does not have enough energy to excite electrons to higher energy levels or cause molecular rotations. Instead, it interacts with bonds, making them stretch or bend in specific ways. So the correct answer here is A. It begins to vibrate. Our last and final question says, radio frequency radiation has what kind of impact on matter? A says it makes electrons spin. B says it makes the molecule rotate. C says it makes the nucleus split. And D says it makes the nuclei spin. Radio frequency radiation interacts with the nuclei of certain atoms, and it causes them to spin when placed in a magnetic field. This is the principle behind nuclear magnetic resonance, or NMR, where radio waves influence the spin states of nuclei like hydrogen or carbon. It does not affect electrons or molecular rotation, and it most definitely does not cause the nucleus to split. So the correct answer for problem 8 is D. It makes the nuclei spin. And with that, we have completed this lecture and the accompanying practice problems. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.